Hello, everyone. So thank you for being here. So this lecture is going to be a little different from the previous ones, which were more, let's say, focused on the theoretical aspects of quantum chemistry. And today we're going to talk about more like practical aspects and like computational aspects. So of course, if you have any questions, so please let me know and I'll stop and try to answer your question. So just a disclaimer here. I'm not going to try to be like exhaustive or formal or anything. I want to give you tools. So I'm going to talk about lots of little aspects, and hopefully it's going to give you a rough idea of what you are able to do. But it's not going to be complete or anything like very formal and so on. So it's more like to help you discover some new tricks and tools that you can use for your own research. And so hopefully you can learn some stuff from this lecture. Okay, so today's program. So basically we're going to start by talking a little bit about the more practical aspects of Hartree-Fock. So I think Vincent talked about it a lot, and so we're just going to pick some precise parts of the algorithm and just try to dissect a little bit more how we calculate those things in a computer. Okay, so we're going to talk a little bit. So we're going to spend a little bit of time talking about how to compute the integrals. Okay, so that's a very important aspect of Hartree-Fock calculation, and that's basically very important because all the rest of the calculation that you're going to do is basically going based on those integrals. Okay, so it's really the basics. Okay, and so we're going to talk about the orthogonalization matrix that Vincent talked about a little bit and how to compute it as well very quickly. The construction of the Coulomb matrix and a trick known as resolution of the identity that is used a lot now in quantum chemistry and in many other places, of course. And how to compute the exchange, like Hartree-Fock exchange, but also DFT exchange, and it's going to be a more practical aspect of what Julien talks about last week. Okay, so how do we compute energies at the DFT level? And in a second time, so we're going to talk a little bit about correlation energy, so how to compute the correlation energy based on different formalism. And in particular, we're going to try to talk about a little bit of how to compute the MP2 correlation energy, so the second order model playset. And so we're going to talk how one very important step in that algorithm is to what we call the AO to MO transformation. So how you transform the integrals of the AO basis to the MO basis, okay? And also so a few tricks like the Laplace transform, and that will bring us to what we call the local MP2 as well, okay? And hopefully we're going to have time to talk about couplet cluster a little bit. So I think Vincent talked about it during his second lecture. And so hopefully we will have time to talk a little bit more about modern like couplet cluster methods and how we compute the couplet cluster with doubles. So that's basically one of the simplest couplet cluster methods, and the algorithm to do this, okay? And the few tricks that you can use to compute this a little bit more efficiently, okay? So that's the only references that I'm going to give. So basically I've tried to pick one reference for each subject that is relevant, but of course it's not an exhaustive list. And if you want to have more details, please grab the reference and have a read, and you should find other papers talking about the same subject, okay? And please, again, stop me if you have any questions. I hope everybody can hear me, so I guess it's okay. All right, so if so, okay, so we're going to start with Hartree-Fock and how do we do that in practice. So this is probably my favorite book, and my favorite page in that book is page 146. And if you look at page 146, it basically gives you the complete algorithm to actually perform an Hartree-Fock calculation. And so when I was your age, I found that pretty cool, because you can basically grab anything you want and do your own calculation and write your own code, which is not something that is easy, but I do recommend all of you to do so, because you're going to learn a lot of things. Okay, so we're going to try to go through that algorithm a little bit. So the first thing you have to do, of course, is specify a molecule. And what I mean by this is that the only thing you have to specify is the position of the nuclei, okay, and their charges, okay. And that's why it is called an ab initio calculation, because that's the only input information that you're going to need for your system, okay. And so one more thing that you need, and we're going to talk a little bit about it later, is the basis set, okay. So that's something very important as well. So the first thing that you're going to do after that, okay, so you basically read your input file, and the first thing you do is to compute a bunch of integrals, okay? And so we're going to talk about it at length after that, okay? So you'll see there is two types of integrals. You have this overlaps integrals S and the co-Hamiltonian, and after those nasty two electron integrals that we call also electron repulsion integrals, or ERI, okay? I'm going to use that term a lot next. So after, you need to compute your orthogonalization matrix that we call usually X, okay? And we're going to talk a little bit about it. So Vincent had a slide about it, but we're just going to talk a little bit more, because I think that's something that is important. So why do we do it? And that's very important to understand. That is that the atomic orbital basis set, so this one there, is a non-orthogonal basis, okay? And so you need to orthogonalize it to be able to compute easily all your quantities. Okay, so this X matrix, thanks to this X matrix, you're going to be able to go from this non-orthogonal phi mu basis set to an orthogonal version of the AO basis, okay? And so you're going to simplify all the treatments. So for the rest, so I'm going to talk about the computation of J and K, which are respectively the Coulomb matrix, or the Hartree matrix, we say in DFT usually, and the exchange matrix. And so if you sum those two terms to the co-Hamiltonian H, you get the Fock matrix. And when you have the Fock matrix, what you do is that you basically, you're going to do a change of basis. So you go in the orthogonal basis thanks to this X matrix. You diagonalize F prime in that basis, and you back transform your coefficient, okay, to have the coefficient of the molecular orbitals, the C's, okay. And after, you can compute your density matrix, and after you loop, and that's basically your SCF algorithm. So it's not very hard. All those steps here, they're just like very basic linear algebra steps. So you basically use diagonalization, matrix product on all those things. So they're very basic. So we're just going to talk about how to compute those quantities over here. Okay. All right. So next, okay. So first thing I told you is we need to compute a bunch of integrals. So there is two types of integrals basically. And so you can have a look at Appendix A in Szabo and Östlund's book. So they basically tell you how to compute these guys in specific cases, in a specific case, but I mean, like, it's general enough for us. So you have the one electron integral. So why do we call it one electron integrals? Is because the integrals does only involve a single electron, so R here, okay? So you have this overlap matrix, which is going to give you the overlap between two basis functions. So if I take that figure over here, so that's one basis function centered on one atom, okay? And I can compute the overlap of this basis function with the other guys, okay? So here you have a P, it's probably a D over here, and F and G, and so on, okay? So you have the same type of one electron integral for the core Hamiltonian, okay? And remember that the core Hamiltonian gathered all the one electron energies of the system, which mean the kinetic energy and the electron nucleus attraction, okay? And the second type of integrals are what we call the two electron integrals or the electron repulsion integrals. And so remember, so it's very important, there is two types of notations in quantum chemistry, okay? So we're going to talk about it. So we call it two electron integrals because that's basically involve the coordinates of two electrons, so R1 and R2 over here. And you have this infamous 1/R12 operator, which is the Coulomb operator. And here what you're going to calculate is really like the Coulomb repulsion between a charge density represented by R1 here, okay, and a charge density represented by R2 over here, okay? And so that's why those notations with those round brackets are called chemist notations, okay? It's because you have this nice physical interpretation where you have two charge densities interacting via a Coulomb interaction, okay? So always remember that the product of two orbitals is a charge density, okay? That's important. And so usually you see also in textbooks that you have these double bar integrals, which basically takes into account the permutation of two indices. So that's usually what you use when you are in the spin orbital basis, okay, to take into account the fact that you have exchange in the system. So it's just notations, but that's going to be important when we talk about correlation, okay. And so you have the more conventional physicist notation or Dirac notation, which does involve like the usual Brown-Kett notations. And again, so it's very similar. So it's just that you put on the left the mu and nu, okay, and on the right lambda and sigma, and you have R1, R2, R1, and R2 instead of having 1, 1, 2, 2, okay. And again, you have this double bar notation as well, which is very common in correlated methods. So here, today I'm going to do everything in first quantized formalism, if you want. And so I'm going to try to give explicitly all the notations and so on. So that's the first time I do this lecture. So I may have forgotten some stuff. So don't be afraid to ask if I forgot something key and you don't really understand. No need to wait for the end of the lecture to ask the question if it's really important for the understanding. Okay. Okay. All right. So when you're going to compute those two electron integrals, okay. So what you're going to do, you have to understand that these guys are basically four center two electron integrals. Okay. So what does it mean is that it involves four functions, which can be centered at four different centers. So you can have A1, A2, B1, B2, for example. So that's the most general case if you want. Of course, they can be what we call concentric, so which mean all at the same spot. But the most general case is that where they are at one each center, okay? And here you have to understand that it's a very complicated quantity here, okay? So when you see those integrals on paper, it looks like a very compact formula, but actually if you look at it, it's very complicated. And formally, and I stress that point, formally, you have to compute n to the 4 ERIs, okay? So what I mean by n to the 4, it means that if I have n basis functions in my system, okay? And I'm going to use that notation all the time. So basically you have n time n time n time n two electron integrals to calculate. So you have n to the 4 ERIs to compute. And if you do it, let's say, the vanilla way, like the very, let's say, the easy way, it's basically going to spend, you're going to spend your entire time doing this. The rest of the calculation is going to be peanuts, okay? So that's something that is, people have worked on this a lot 10 or 15 years ago, or 20 years ago even. And you have to develop very, very efficient algorithm, because if you don't, basically you're going to spend your entire time basically computing integrals, okay? So that people have spent a lot of time making very, very efficient algorithm to compute these guys very, very fast, okay? So what you have to understand as well is that in most basis set that we call Gaussian type orbitals basis sets, so GTOs. So basically, when we talk about STO, 3G, 631G star, CC, PV, DZ, and all those basis sets, that's Gaussian basis sets. So it means that your building block, your Lego, is basically going to be Gaussian functions, okay? And so there is two types of GTOs, and you always have to remember that, is that when we write an integral like this, actually, that's what we call contracted GTOs, okay? Which means that those functions are already a linear combination of primitive Gaussian functions, okay? Those A's with a square bracket here. So let's take an example. For example, if you take the STO of 3G basis, okay, for the hydrogen atom, so the contracted function is going to be this guy here, okay, the black guy, okay, and actually this function, sorry, is going to be a linear combination of those three colored functions that we call primitives, okay. So they're going to have a different exponent, okay, alpha. Okay, so the exponent of the Gaussian function, remember, it's basically how tight is the function. If alpha is large, you're going to have a very tight function. And when alpha is bigger, basically you're going to spread the function. Okay, so why we do this is because usually what we should use is basically, at least in molecules, is Slater functions. But if you use Slater functions, basically you're going to have troubles to calculate all the integrals, because you need very, very complicated formula to compute them, and you don't really want to do that. By using Gaussian function, it's much, much faster, okay? So you really want to use Gaussian function, and you're going to try to approximate a Slater function, okay, with Gaussians. So what you can see here is that your contracted basis function here is the product of three primitive Gaussian functions, and they have different exponents. So you have, for example, the red one, which has the smallest exponent. So it means it's tight, and it's basically its value, most of its value is at small r. And after you have what we call a mid-range Gaussian, so the blue one, which is going to approximate that function at mid-distance here. And you have this green guy who has a very small exponent, or smaller exponent, which is going to approximate the long-range behavior of that function, okay? So with few Gaussian bases, we can basically try to model a better Gaussian basis function, which resembles more a Slater function, if you want. Okay, so a primitive Gaussian function has basically three characteristics. The first one is the exponent, so we just talked about it. The other one is the center, okay? So it can be centered at different places in the molecule, and most of the time it's basically centered on the nuclei, okay? And you have the angular momentum, okay? So the angular momentum basically is three integers. It's going to tell you, if you take the sum, it's going to tell you if it's a S function, if A equals 0, or P function, if A equals 1, or D function, if A equals 2, and so on, okay? So usually it's the sum of the three integers that gives you what type of function you have, okay? So if I come back here, so here you can see that you have the shape of a P function, okay? So here is basically going to be a PZ function, okay? And here you have a D function, and you see that the shape is different. So you're going to be able to polarize the electronic density to try to catch the overall shape of the density or the wave function, if you want, okay? So that's the idea. Okay, so what you have to understand is that to compute one contracted ERI, you need to compute many primitive ERIs, and that's very important to understand that. So just to make sure we understand each other, if you want to compute a contracted ERI, which is a linear combination of primitive ERIs, you see that basically the contracted and the primitives, okay, have the same center, okay? You always develop the function at the same center. You have the same angular momentum, that kind of makes sense, but you have different exponents to be able to model properly the shape of the function that you have. And you have different contraction coefficients. So that's basically the coefficient in the linear expansion, okay? And so that's given to you when you use a basis set, okay? So you don't have to obtain them variationally and so on. It's given. That's some input quantities from the problem, okay? So what you see here is that if I want to compute one contracted ERI here, basically I'm going to have a quadruple sum over the primitive ERIs, okay? Remember that a contracted ERI is just a linear combination of these guys, okay? So basically, if I take just one example, okay? So if I take the CCPBTZ basis set from the carbon atom, which is given here, okay? So for example, you model the first S function, okay, by 10 Gaussian functions. So here, that's the exponents, the first column here. And here, that's the contraction coefficient. So that's the format that you're going to use to do your calculations. So that's the format of your basis set. So what does it mean here is that if you want to compute the 1s, 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 1s ERI in the carbon atom, what you need to do is you need to compute all those integrals over here, okay? So there is 10 to the power of 4 S-type integrals to compute, primitives 1, okay? So what does it mean? It means that you need to be able to compute that guy very, very efficiently, okay? Because if you want one contracted one, you have to compute 10 to the 4 primitive ones, okay? And that's something that is usually not said, but it's very important, okay? There is no question so far? No? Okay. Okay, so it looks like it's very hard, but actually there is a few properties from the Gaussian function that are going to save the day, basically. And so basically the most important rule of Gaussian function, okay, is what we call the Gaussian product rule, which tells you that the product of two Gaussians is actually a Gaussian function as well. So, so it's a very basic problem, and you can do it at home if you have time, okay? So if you take a Gaussian function with an exponent alpha and a center A, okay, S-type, and you take the same one with an exponent beta and a center B, okay, you do the product of them for the same R variable, that's important, R here, R there, okay? So you can show that you can write that product as a Gaussian function with an exponent zeta, which is basically the sum of the two exponents, and a center P, which is just the center of mass of A and B, with weights given by the respective exponent of those two Gaussian functions. Okay, so that's cool. But what is even cooler is that basically in front of that you have this prefactor here, K, which is given by this. And that exponentials, what is very important with that exponential is that term here. Because that term is going to tell you that if A and B are far away from each other, okay, this product is going to decay exponentially, okay? And so what does it mean? It means that if I have two Gaussian far away, if I take the product, it's going to give me another Gaussian, but with a prefactor that is very, very small and decays exponentially with the distance, okay? And so if I apply this to my two electron integrals, okay, so what I'm going to show is that if I take two electron integrals A, B, C, D in chemist notation, okay, so I can do a Gaussian product rule on A and B and a Gaussian product rule on C and D. and I can basically contract my two electron integral as a easier two electron integral over where I have only two Gaussian functions, one with exponent zeta and center p, and the other one with exponent eta and center q, given by the same formula. And in front of it, and I should have put that, I have a k square factor. I need to correct that after. So here you have this k factor in front of it that I've forgotten. And this k factor is going to be very important because it's going to show you that your integral is very small if a and b are far or c and d are far. So basically, I told you before that formally you have n to the 4 ERI to compute, but thanks to the local nature of Gaussian function, actually in a large system, you only have a quadratic number of two electron integrals that you have to compute. And that's super, super important because here it tells you that basically you're not going to spend all your time computing ERIs when you do your calculation because there is only n squared to compute, okay? But you have to do that, you have to realize all those things that I showed you before. And you have to design your algorithm to take that into account and to make sure you do not compute integrals that are small. But you need to know that a priori, okay? And that's the important point. Okay, and so to be able to not to compute those small integrals. So
Pierre-François, excuse me, sorry. There was a question about notation. I think it's important to answer because just to clarify things. Can you see the question about the R? So Lucas is asking what it is. So it's I mean, these are the electronic coordinates, right? But he's asking if it's the center of mass of the molecule, which is completely a different thing.
No.
Yeah.
In equation 11 of the slide is R in the same R in the center. No, so all those variables here are dummy variables. They basically, so you're going to integrate over R, okay? So R take all the value in space. So A is a point in space where it can be basically centered in one atom, but it can be anywhere. You are allowed, if you want, to put a basis function in between two atoms. There is no problem. Is that it's basically, always remember that basis functions are like Legos, okay? So basically I give you a box of Legos, and if I give you very small Legos or with weird shapes, you're going to be able to compute, to design like very weird shape of dinosaurs and so on. And if I give you only like big blocks, square, you're not going to be able to do some very nice shape. So that's exactly the same here. Okay, so R is not the molecule center or anything like this. It's a variable in R3 if you want, and you're going to integrate on that. Okay. Does it answer your questions? Sorry. Good. Okay, so I'm going to try to leave the chat open somewhere so that I can see it. Over here. Okay. Okay. So as I told you before, so basically you want to avoid computing an integral when it's small. Okay. But you need to know that before computing it, because if you have to compute it and after look at the value and say, well, it's small, throw it away, it's a bit pointless. So if you want to know in advance, if you want to have an idea of the magnitude of the integral, what you can use is upper bounds, and mathematics has been working on upper bounds for centuries now. So we can use that. And so basically you look for a number b that's going to tell you if your integral is less or equal to that estimate p, okay, in absolute values, okay? So if you want to have a good upper bound, of course, you can design upper bounds, but you need to design them as efficiently as possible. And to do that, so your upper bound must be tight. So what I mean by tight, it has to be a good estimate. So if you tell me that all the integrals are less than than 10 to the power of 15, I'm going to say, well, it's not very useful, okay? So you need to have something a little bit better, sorry. And another important property of upper bounds, they need to be simple. So what I mean by simple, I mean that they have to be cheap to compute, okay? Because if your upper bound is actually more expensive than the integral itself, it's a little bit annoying, okay? I prefer to compute my integral than your upper bound, okay? And another point that might be useful to know is that I need to compute a small number of upper bounds. If I can screen all the integrals with a smaller number of upper bounds, that's even better, okay? So we can use, and that's pretty much used in any quantum chemistry software these days, because it's very, very easy to implement, is what we call Cauchy-Schwarz. Okay, so it's the usual upper bound that you see in first year mathematics when you start talking about norm and so on. And so Cauchy-Schwarz tell you that in absolute value, you can have an upper bound of the value of the integral by taking the square root of two very similar integrals, okay? And if I use those P and Q, those center of mass quantity, actually I can show that the upper bound of PQ is just the square root of those guys here, okay? So what is nice is that by computing a linear number of integrals, because there is only a linear number of those types of integrals, I can actually screen n square of them, okay? So that's very nice, because by computing a small number of integrals, I can screen pretty much the entire ERA of the system, okay? So it's a very nice bound. So can anyone tell me if there is a problem with that bound? Can you see a problem with this bound? There is a very specific scenario where it's going to fail. Can anyone see it? Can put a little message in the chat box if you see it. If you have fast finger. No? Okay, so the main problem with the Cauchy-Schwarz bound is that it's going to be blind. It's not going to be able to tell me if the center P and the center Q are far away from each other, okay? So just before I told you that if A and B are far away, your integral is going to be small, but you can also compare the center P and the center Q. And if you have a very, very large molecule and the center P and the center Q are, let's say, 100 angstroms away, okay? Of course, the interaction of P and Q, even if it's a long-range interaction with 1/r, basically this integral is going to be very, very small, so you don't have to compute it, okay? But Cauchy-Schwarz cannot see it. Why? Because Cauchy-Schwarz only use quantity specific to P times quantity specific to Q. So there is no distance information in that bound, okay? So you're not going to be allowed to see that some of them are 0 because they're very, very far away. And so you can design bounds that see that. And for example, you can use the generalization of Cauchy-Schwarz bound, which is called the Holder's bound. And so I don't know if you saw that in mathematics, but when you have the square root and square root, it's not the only norm that you can create in an Euclidean space. You can also actually use different value for m and n. So Cauchy-Schwarz would correspond to m equal n equal 2, but you can take any m and n such that m and n is greater than 1, okay? And so by varying m and n, you can create different type of bounds. And so you can take m very large and n equal 1, for example, or 2. And so you can design bounds that are going to see that if they are very far away, actually, you're not going to be, you don't have to compute that integral. Okay, so that's what we call the locality of the electronic matter. Okay, so that's a very important concept in linear scaling methods. If stuff are far away from each other, they probably don't talk to each other, so you don't have to worry about them, and you can discard them without any significant error in your calculation. Okay. All right. So I'm going to give you numbers. So here, remember that when we write this integral a, b, c, d, here in between we have an operator, a 2-electron operator. So most of the time we have this 1 over R12, which is the Coulomb operator, okay, which is the distance between R1 and R2 in absolute value, by the way. And you can see, so if I take like polyenes molecules, okay, so propene, butadiene up to dodecahexane, which is large. So I take like, I think it's the 631G basis set, okay? And so I increase the number of carbon atoms in my chain, and I look at the number of significant 2-electron integrals, okay? So what I mean by significant is the number of integrals that are greater than a given threshold, usually taken to 10 to the minus 15 or so on. That's usually pretty good. And what you can show is that if I look at what is the scaling, the number of integrals that I have, okay, you see that slowly, when you increase the size of your system, it does go to something quadratic, okay? So if you see in textbooks, if somebody tells you that that you have n to the 4 2-electron integrals to compute, you should tell him, no, it's wrong. You have a quadratic number if you have a large enough system. Of course, if you do the helium atom in a very large basis, you're going to have to compute n to the 4, roughly. But if you have a long molecule or a very large one, you're not going to compute n to the 4. And that's why you can do DFT calculation and Hartree-Fock calculation on very large systems. It's because of this. Otherwise, you wouldn't be able to do it. Okay. And so, if you use a different operator, like let's say, like here, it's a Gaussian Geminal operator. So it's a Gaussian, but with a 2-electron quantity inside. Okay, and that's a very short range operator, not like the 1 over R12, which is fairly long range. You see that in that case, you even go to a linear number of 2-electron integrals, okay? So that's something very important. Depending on the operator and the locality of the basis function, the number of 2-electron integrals that you're going to have to compute is going to be different, okay? So what time is it now? 40. Okay, so quickly, so if you want to compute 2-electron integrals, there are 3 things that you're going to have to be able to do. You're going to have to compute very efficiently those what we call fundamental integrals, okay, which are basically the S-type integrals, a generalization of the S-type integrals. You need to use recurrence relations, so you're going to increase the angular momentum in your integrals with recurrence relations. That's the way of doing it efficiently. And the third ingredient that you will need is upper bounds to be able to skip the calculation of the integral that are small, okay? So that's the 3 main ingredients. Okay, I'm going to skip this because I don't really have time to do it. All right, so that's all I wanted to say about 2-electron integrals and so on. So if you have any question on that, maybe that's the moment to put it in the chat box that I can see now. Otherwise, I'm going to talk a little bit about the calculation of the orthogonalization matrix. Okay, so that's the matrix X. And as I told you, what you want is to compute an orthogonalization matrix, which makes your AO basis orthogonal. So basically, what we want to do is to compute this. Okay, so that's basically the definition of the X matrix. So what it tells you that if you take the metric of the space, of the AO space, you want to make it 1, okay? So you want to make it orthogonal, okay? And so to do that, normally, we compute S minus half. So for people who are not very comfortable with linear algebra, sometimes when you have power of matrices like this, it's a little bit unsettling, okay? So what we mean by this is that the power of a matrix, and that's the only thing I want to tell on this, is that you're not computing it by just taking all the inverse square root of all the elements of your matrix, okay? So what you usually do, you diagonalize S. That's going to give you some U, a matrix U, which is the matrix of the eigenvectors, okay? and the matrix S, which is going to be a diagonal matrix with the eigenvalues on the diagonal, okay? When you have this diagonal matrix, you can take the inverse square root, okay, of those elements if they are not too small and if they are not negative, okay? And normally S is a positive definite matrix because it's a metric, and so you don't have any problem. But if you have linear dependencies in your basis set, you're going to have trouble, so you have to be careful, okay? And I think after you're going to back transform this S minus half with this U matrix, so always remember that the matrix of the eigenvector is a transformation matrix from the representation where the matrix is not diagonal to the basis where it is diagonal. So you can back transform that S minus 1 minus half matrix to the original basis to get this S minus half. And you can check after that, thanks to this matrix, you can orthogonalize the matrix. Okay? And if you have linear dependencies, you can use different recipes. That's in Szabo and Assum's book, if you want. And for example, you can use what we call the canonical orthogonalization, that for which you are able to take into account those linear dependencies and get rid of them. Okay, so have a look at this. If you have very big basis, you have to be careful. Okay. All right, so now let's try to talk about calculation, the different quantities that you have to calculate during an Hartree-Fock calculation. So, so the first thing, so the central quantity here is the Fock matrix, so F, and basically F is going to be composed by, of course, the co-Hamiltonian here, but by two other quantities, which are what we call the Coulomb matrix and the exchange matrix, okay? And basically computing those two quantities is going to be very central in the Hartree-Fock algorithm, okay? So P here is just the density matrix, okay? So basically it's so if you have a closed shell system, it's just the sum of the product of the molecular orbital coefficients, okay? And basically when you have this matrix F, okay, that you compute like this, you can basically compute the energy, the Hartree-Fock energy, just by computing the trace of a matrix product. Okay, so it can be done efficiently. So what I want to show you here is that basically one needs to be able to compute F very, very efficiently, okay, or as efficiently as possible at least. Okay, so let's do a little bit of programmation, or let's say a bit of it. So for example, if I do like very, very basic, if I write my very basic Hartree-Fock program, what I'm going to do is that I'm going to say, okay, I want to compute J, and J is given by this expression here. Okay, it's not very hard. So what I need to do, I need to compute all the elements mu, all the elements nu, okay? And I need to sum over lambda and sigma, okay? So I'm going to do 4 loops, okay? I'm not going to forget to put J mu nu equals 0 at the start so that I can accumulate that quantity over here. So after, I'm not going to write it down, but don't forget that part, otherwise you're going to get rubbish. Okay, and I'm going to accumulate J. Okay, and I'm going to sum over lambda sigma. Okay, I'm going to sum on the 2 electron integrals. So J, you see that you're contracting over the coordinate of 1 electron. So mu nu is, mu lambda sigma is electron 2. Here it's electron 2, and I'm going to get a 1 electron quantity. Okay, and so that algorithm is an n to the 4 algorithm. Why? Because it does involve 4 loops. Okay, of a mu nu lambda x sigma. So I'm going to do n to the 4 operation. So it's going to cost me n to the 4. Okay, so that's very basic programmation. So that's going to be very expensive if you do it like this. So so people have designed tricks to do it faster. Okay, lots of tricks actually. And so one of them that I want to talk today is the resolution of the identity, which are many, many different names depending on how you do things. So there is many, many variants. I'm not going to talk about them today, but there is many different flavors of Ri, so resolution of the identity. And so I usually call the Ri approximation as a fancy way of writing one, is that if you have a complete basis, okay, and that's what I mean by this infinite sum here. If you do that summation, okay, it's going to give you the identity, or one if you want, okay. Of course, it's always hard to build an infinite set of functions, or a complete set of functions at least. So usually you're going to build a basis set which has basically k basis function, and you're going to make sure that you can write one as efficiently as possible, okay? So that's what we call an auxiliary basis in calculation. So it's not the AO basis, it's a different basis, okay, which is also usually atom-centered, that is going that you're going to use to compute quantities more efficiently, if you want, okay? So just we can take the example of the Coulomb matrix here. So that's its definition again. And so what I can do, instead of this vertical bar here, I can introduce my resolution of the identity over here. And now I can factorize the different terms differently, okay? So I can take those blue terms here and I can put them together. And now this quantity, I'm going to be able to compute that as in k n squared operations. Why k n squared operation? Because I'm going to compute all the A elements, okay, and I'm going to sum over lambda A sigma, okay. So here I have n square elements, and here I've got k elements, okay. So it's going to cost me k in storage because I'm going to have to store those elements here that I'm going to call I, okay. That is only going to cost me k n squared, which might be smaller than n to the 4, usually smaller than n to the 4, okay. And so after that, when I have stored that intermediate quantity, I can compute the second term again in k n squared, okay? Because again, I'm going to sum over A, and I need to compute all the elements mu nu. So it costs me k n squared. So here you've been able, and that's a very general procedure, you've been able to split the n to the 4 in 2 times k n squared plus k storage, okay? So now you're going to be able to do much larger calculations, okay? And that's used in many different methods these days, okay? And if you are even smarter, you can use the locality of the electronic density, because I told you that if lambda and sigma are close to each other, okay, are very far away, they're going to die. So basically there is not n square of these guys, there is only n, okay? So you can even play other tricks, okay? So here that's the very general, let's say a very general Ri example, but you can find some more effective approaches. So Cholesky decomposition, low-rank approximations, okay? So they're all based on the same idea, is to approximate, to have an auxiliary basis to help you doing the calculation, okay? So that's something that is very fashionable in quantum chemistry these days, and not only in quantum chemistry, by the way, okay? Okay, now we can talk a little bit about the exchange matrix. So it's a very similar quantity, okay? So again, so the only difference with J is that you permuted this lambda, this sigma and nu quantity, okay? So formally, again, it's n to the 4 algorithm, and you can try at home. If you want to play, you can't use like, you can, but basically you can't really use the Ri technique for that term. Why? Because you have this permutation here, which is annoying, and so you cannot dissociate the 2 terms nicely and compute that with intermediates and so on. So it does cost much more than the Coulomb matrix, and that's why, for example, in solids, the people don't really, well, now they do, but for a long time, people were not doing too many Hartree-Fock calculations because it was very expensive, okay? And so basically, what you can do DFT, like Julien talked about the last 2 weeks. And in DFT, the exchange is local. So now you can play games again, okay? So if you remember Julien's lectures, okay? So if you take the simplest approximation, so I take the LDA exchange, okay, which is just given by the Slater-Dirac functional, which is just Cx, that coefficient times rho to the power 4/3, okay? So you can write, so if you look at the expression of the elements of the exchange matrix, you see that it's just a one electron integral this time, okay, because it's DFT and it's local. You have this LDA exchange potential, okay, that you integrate with two basis functions, mu and mu, okay. So the exchange potential is just the derivative of your exchange functional with respect to rho, okay? So you just 4/3 Cx rho to the power 1/3. And so now you have to compute those quantities here. Okay, the problem is that it's not like the two electron integrals or the one electron integrals in Hartree-Fock. You cannot do that in closed form. Okay, so by closed form, I mean analytically. Okay, why? Because the power of 1/3 is actually a tricky quantity to deal with. Okay, so you have to use different tricks to compute that integral. So in practice, if you do a LDA or a DFT calculation in general, what you're going to use is you're going to use integration grids. Okay, so you're going to take R3, so the space of your molecules, and you're going to make a grid, an integration grid, and you're going to use this grid, thanks to a quadrature, okay, to compute those integrals numerically. So a numerical integration via quadrature, what is it? It's a set, so you're going to approximate an integral, for example, f of x dx, by a sum, so a discrete sum of a k. And so you're going to have two important quantities, is the weights, okay, and the roots, okay? So that's the two important quantities. So the roots are going to the point of the grid, so the Cartesian coordinates of the point of the grid, and the W's are going to be here, so the weights, that's going to be a single value for each point that are going to give you the weight that you should give to that point to approximate nicely the integral, okay? So that's basically what it is. So if you use a quadrature to compute those k elements here, so what are you going to do? You're going to write this integral here as a sum, so you over the number of grid points, okay, which can be increased if you want to be more accurate. Okay, you are going to have those weights and those roots. Okay, the roots here is basically what you have to do is to compute the density at the grid points. Okay, so that's easy because you just have to compute the value of the AOs at those grid points. Okay, and if you have the density matrix after, you can compute rho at each grid point. And if you look at how much does it cost to do this, it costs n grid times n squared, okay? So it's much less than n to the 4. So when you have computed this, now you can use it here to compute the elements k mu nu, okay? So you have those quantities, okay? And you sum that, and again, it's going to cost you n squared n grid. So why is that? Because you have one summation here over the grid points, and you have to compute all the elements mu and nu. So it costs you n squared times n grid. Okay. I hope it's clear for everyone. If it's not clear, just let me know. I'm very happy to say it again. Okay. To explain further. So if you do DFT, local at least, and basically if you do GGAs, you can use the same tricks. Instead of spending n to the 4 computer time doing that, you can do that in n grid times n squared, which is a massive saving. And that's why, for example, for solids, DFT was so more fashionable than Hartree-Fock, for example, because the exchange can be computed very, very efficiently. Okay.
Pierre-François, can I? can I ask you a stupid question?
For sure.
So it's about the resolution of identity. I'm sorry. So you used the resolution of identity, or let's say the closure relation, as if you were having bra and cat, but there is these are two electron integrals, so there is the 1 over R1 too.
Yes.
So I was wondering, is there something hidden there, or?
Yes. So I didn't want to talk about it.
Oh, sorry. Oh, because you do. Okay.
Yeah, no, you're right. So Emmanuel is saying that I'm cheating here because the bar is not a 1. It's a 1 over R12 operator, so I should be more careful. And he's right. But so that's what we call Coulomb matrix or overlap matrix for the resolution of the identity. And actually, when you write that expression here, you can generalize it for any 2 electron operators, right? Actually, all nicely behaved 2 electron operators. So basically, you can, if I write this one as a delta function over R12, so actually you can generalize that to any 2 electron operator, and you can do a Coulomb fitting to actually replace that bar by the 1 over R12 operator. So it's a totally general procedure that can be applied to Coulomb operator, overlap, and anything in between. If you have a Gaussian Geminal, Slater Geminal, or anything you like. Yes. But
okay,
you're right, I've cheated here.
Okay, thank you very much. There is another question in the chat box, actually.
Can you say again what is the difference between xk and the roots? Thanks. Okay. So here a quadrature, so it's a quadrature rule. Basically, you want to approximate an integral, which is a continuous quantity, if you want. So you want to approximate this by a sum, okay? And so there is 2 important quantities. So there is those roots, xk, which are basically the points where you're going to evaluate your function in space. But actually, depending on the shape of your function, you're going to design weights. So basically, that's going to be just a single real numbers that are going to be given to each point, okay? That is going to be used to actually weight what is the importance of that point in the integral, if you want. So for example, if you have an electronic density, for example, I have like 1 helium atom here. And so you know that the density basically is going to be like this. It's going to decay very fast and goes to 0 when R is large, okay? So you can imagine that in your integral, the weights that are going to be far away are going to be small because it doesn't contribute too much to the integral. And the weights that are going to be close to the nucleus are going to be large. And so basically those weights, they are input quantities, okay? They are designed to reproduce as best as possible the integrals. And you're going to use them to approximate your integrals, okay? So depending on the shape of the function that you're going that you want to integrate, basically the weights are going to be different. So quadrature is based on the what we call so it's the orthogonal polynomials, so Legendre polynomial, Chebyshev polynomials, Laguerre polynomials. And basically, each family of polynomials is going to be used, for example, depending on the shape of your function. So if you have a function which is basically a polynomial between -1 and 1, you're going to use what we call the Gauss-Legendre quadrature, okay? If you have something which looks like a Gaussian function, usually you're going to use Gauss-Hermite, okay? Because Hermite polynomials are orthogonal polynomials for a weight which looks like a Gaussian function. If your function is between 0 and infinity, it looks like a Slater function, exponential function decaying, you're going to use the Laguerre polynomials, and so on, and Chebyshev for other stuff. So depending on the shape of your function, you're going to use different quadrature. For molecules, for example, people have designed quadrature rules for specifically for the electronic density, okay? So usually it's what we call Lebedev rule for the angular part, and where there is different type of rules for the radial part, which are called Euler-Maclaurin and so on. But there is different families of quadrature rules that you can use. Okay, somebody else. could you use the decomposition of P to form of the action stem? So I don't think so, because if you have a look at the reference I give at slide number 2, I think even if you decompose the density matrix with the coefficient, I don't think you can factorize everything the right way. So you can lower the cost of the exchange, of the calculation of the exchange with resolution of the identity, but you cannot break the scaling, the overall scaling, I think. So, so the literature is pretty big in that research area. So maybe you'll find something, but I don't think it's easy, at least. So the auxiliary basis for the Ri, so they usually are Gaussian functions. Okay, so they're basically atom-centered Gaussian function, S, P, D, M, F, G. Usually they have higher angular momentum because you need to be complete. Okay, for example, if you do a Hartree-Fock calculation or a DFT calculation, basically you don't really need to be complete in the virtual space. And why is because when you do an Hartree-Fock calculation or a DFT calculation, you only actually converge the occupied orbitals. Okay, but if you use the resolution of the identity, normally you have to have a complete basis. And so normally it depends on the cases, because so you have tailored auxiliary basis for the Coulomb matrix, for the exchange matrix, and for F12 methods that are explicitly correlated methods, you have like some different bases. So depending on what you want to approximate, people have designed different basis sets, but they are still atom-centered Gaussian basis sets. So which means you can still use the same tricks to compute the integrals, and that's very important. But you have more integrals to compute, okay? And usually the auxiliary bases are much larger than the AO basis, okay? You basically don't span the same space if you want. And so what I haven't told you, but maybe I should tell you here, is that you see that if you use the resolution of the identity, here you only have 3 centers integrals to compute, because now all your quantities can be written at 3 centers, and you don't need the 4th center to compute the quantities. So it can be a very significant saving as well. Okay. Okay. So now let's try to move to correlation. Okay. So what time is it? Okay, not too bad. Okay, so for example, let's take the simplest. So if you want to catch a good chunk of correlation at not too much cost, actually, you're probably going to use MP2. Okay, so MP2 is a very well-known method, and it's very easy to write down the equation and so on, and to code as well. So usually people use this. Okay, so if you write down the MP2 correlation energy expression, okay, you have a sum of the ij, A and B. So ij are occupied orbitals, okay, AB are virtuals. And basically what you're going to do is you're going to sum over a bunch of 2 electron integrals. We know that now, divided by difference in energy, in 1 electron energy. So the epsilons are basically the molecular orbital energies, okay? And so just to let you know, usually we split that into a direct part, okay, which corresponds to that very nice Goldstone diagram here, and an exchange part where you have this swapping of A and B here, which corresponds to this exchange diagram here, okay? And so you're going to tell me, oh, it's easy. There is 4 sums. It's going to cost n to the 4, because I'm going to do 4 loops, and that's it. And I'm going to tell you, yes, you're right. But there is one step that you forgot. Okay, so if I write down a little pseudocode for the MP2 energy, I'm going to stick EC2 equals 0 at the start, just to make sure I don't get rubbish. I do 4 loops over occupied, virtual. Okay, I compute my denominator, and I just sum over ij and b those quantities, and that's it. Cost n to the 4. Okay, so I'm going to tell you, yes, you're right, but we forgot something, is that those integrals over here are not integrals in the AO basis. They are integrals in the MO basis, okay? And that's a massive difference. So why is that? Is because if I write down the expression of MO integrals PQRS, general one, in terms of the AO integrals, I'm going to write it down as a sum of a mu lambda sigma, C mu P, C mu Q, C lambda R, C sigma S, mu lambda sigma. And here you should scream very, very loud. Please don't do it, but you should. Why? Because if I take that expression here, that mathematical expression, and formally I write my pseudocode to compute these guys, I'm going to have to compute 8 loops. And so 8 loops goes to n to the 8th. And I tell you that if you code MP2 like this, you won't do much quantum chemistry with that. Okay, it's very, very, very expensive. Just to give you an idea, if you do it like this, it costs as much as CCSDT. Okay, so it's probably not the way of doing it. So there is a very nice trick to do that, and that's been developed by Frisch, Ed Gordon, and Popol many, many years ago. It's called a semi-direct algorithm, and I want to talk about this because it's a very, very, very general concept in quantum chemistry that is used a lot, and we used it for the Ri just before, but we're going to use it again. So the idea is just, instead of doing the calculation in one shot, which is going to cost me n to the 8th, I'm going to split that calculation in 4 steps. And each of that steps is going to cost me less than the overall costs, okay? So I'm going to do the first sum, the second sum, the fourth sum, and so on, okay? To get the quantities I want, okay? Mind you, those PQRS quantity, you probably need them for any correlation method that you want. Okay, you always need those integrals in the MO base, so it's very important. Okay, so the step number 1 is going to say, okay, what I'm going to do, I'm going to allocate a temporary array I of size n to the 4. Okay, and so I'm going to do the first summation only. Okay, so I do a sum of a mu lambda sigma and just 1. MO index S, for example, and I'm going to do I, I'm going to accumulate I, that quantity here in I. So if I write that, it's written like it's n to the 5, okay? Because there is 5 summations, and it's going to cost me n to the 4 in storage, okay? Because I need to allocate that array here, okay? So now that I've done this first step, I can do a second step, which is the second summation of a lambda and R here, okay? So I can do it again. So step number 2. So I'll allocate another array, J of size n to the 4 again, and I'm going to do 5 loops of a mu lambda R and S now, and I'm going to accumulate over lambda R, okay? So here I'm going to reuse the I array that I allocated just before, and I'm going to accumulate in J, okay? So now I've got, and that's going to cost me n to the 5, and again n4 in storage, because I need to allocate a second array of size n to the 4, okay? So now I can do step number 3. So step number 3, remember, that's the blue summation, okay? Blue summation, okay? So now that I've accumulated I in J, I is free, okay? So I can reuse it, okay? So I don't have to reallocate any storage, okay? I can still use this I array that I've used in step number 2. So I'm going to accumulate over mu and q, okay? So n to the 5 algorithm, 5 loops, and no new storage because I can reuse the I array that I used at step number 1, okay? And so now you understand how I'm going to do step 4. Step 4, I'm going to use this I array and store everything in my final result and do the last 2 summations. So again, it's 5 loops because n to the 5 and no new storage because I've used the final result here. Okay. So here, what you've been able to do, you've been able to take an n to the 8 algorithm, split it in 4 steps, and each step costs n to the 5. Okay, and with storage, it's important. So it's very general. You've sacrificed a little bit of storage to actually kill that n to the 8th, that horrendous n to the 8th scaling to n to the 5 scaling. And I can tell you that with something like this, you can do lots of quantum chemistry. Okay. And so when people say MP2 cost n to the 5, they talk about this AO to AMO transformation of the 2 electron integrals and not the actual computation of the MP2 number, which only costs n to the 4. Okay. So one last thing that I want to tell you, and I'm not going to tell you much about it, but I just want to give you like a little taste of it, if I can, is what we call so almost trick, okay, that use a Laplace transform, okay. So if you look at the expression of the MP2 energy, what you don't really like is actually this this denominator here, because it basically stops you to actually factorize the expression of the MP2 energy. So one idea that Alnov got a long time ago is to write 1 over delta, where delta is the denominator here, as an integral, okay, of exponential minus delta t dt. Okay, so that's an exact expression. That's what we call a Laplace transform of 1 actually. And so if you use this in the MP2 expression, you can write your denominator like this. And by doing this, now you can actually contract the molecular orbitals with those factors. Okay, the exponential, you can write it as a product of exponential. Jesus. Okay, and you can write that expression like this, where basically for each MOP, okay, you made it like t dependent by including that exponential factor which depends on t and epsilon. Okay. And so by doing this, normally what people usually do is that they approximate this integral with a numerical quadrature to compute that on a grid. Okay. So again, quadrature means you're going to include weights, okay, W, and roots. Okay. So basically, it's going to give you the value of t for which you need to compute those molecular orbital integrals, and the value of the weights. Okay, and you can basically design the grid just for that purpose, so you can make it very, very efficient. And so basically, you're going, and after this, you can even play more games, and you can use localized orbitals, or you can use resolution of the identity. You can use stochastic sampling. And you can use more quadrature by rewriting all those integrals in a different way. So after that, you can play many, many games. But so the idea is basically to actually kill this 1 over epsilon here, thanks to the Laplace transform, and actually after factorizing all the terms. Okay, and you can use that trick for many, many different methods as well. Okay, so that's what I wanted to tell you about this. So basically, that's the first step of local MP2 methods. Okay, it's because here now you can use localized orbitals, and you can use the locality of the electronic density, and you can put cutoffs and so on, and make a very cheap MP2 calculation. Okay. All right. Is there any question? Is it possible to compute other MP2 properties like density matrix in AO basis by Laplace? I have no idea. Seriously, no, I don't know. I can't tell you. Is there any other questions before I go to couplet cluster? What time is it? 17. We are on time. How do you choose your grid? You choose your grid to basically do the best job you can. So basically, usually people design their own grid for their own purposes. Okay, so that's how you make a grid. So I don't know how much I can tell, but so normally what you want to do when you design a grid, if you want to minimize the number of grid points, okay, and so normally there is a few tricks to actually design nice grids, but sometimes depending on the system and the correlation regime, basically you might need to increase the number of grid points and so on. Okay, it's like in DFT, for example, you have different type of grids, and depending on the number of points in the grid, you have more accurate results. So if the grid is very large, usually you have very accurate results. And that's nice because so we rely on energy density in chemistry. And so if you use the same grid for your two calculations, okay, so usually you have a good compensation of error. But you should never use a different grid for if you want to compute a reaction energy or something like this. You should never use two different grids for the two calculations, otherwise you get rubbish. Okay, so you have a compensation of error on the energy by using the same grid. Any other questions? Okay, cool. Okay, now we can talk a little bit about couplet cluster. So I think we're going to finish on this. It's going to take a while. So if you have any questions, please stop me, we have time. Okay, just to start. So couplet cluster comes from nuclear physics, and that's bit imported in quantum chemistry and went back to actually nuclear physics because it's been developed a lot in chemistry. So the idea is that by using an exponential ansatz of the wave function, okay, you're going to be able to include all correction of a given order to infinite order. Okay, so that's different from the linear ansatz in a configuration interaction calculation, where you have a linear ansatz of the excitation operator. Here you exponentiate those quantities to have a type of renormalization, if you want. And so two things you need to know about couplet cluster energies is they are size extensive, which is very different from truncated CI calculation, which are size inextensive, okay? So which means that you're going to lose some correlation energy when you go to bigger systems, okay? So the good thing about couplet cluster is that basically you recover, so I think it's the correlation energy that you recover scales linearly with the number of electrons, so it's always nice. But you lose the variationality of the energy, which means that the couplet cluster energy is non-variational, which means it can be lower than the full CI energy, okay, than the exact energy, okay. So in practice, it's not too dramatic, and that's why it's been used a lot in quantum chemistry, because actually you are size extensive, you get very, very good results for very small excitation degrees, and the non-variationality of the energy is actually quite small in practice, okay? And that's why it's known as the gold standard of quantum chemistry, at least for weakly correlated systems. If you go to strong correlation, well, you're going to have some pretty bad result with couplet cluster, especially if you use like perturbation theory to get some parts of it, okay? But for weakly correlated systems, ground state, you get very, very good results. Okay, so quickly, just to give you a few equations before talking about the algorithm. So you have this, so in couplet cluster, the specificity is that you're going to exponentiate the wave operator t, okay? And so that the wave operator is here, and that's an exponential of the excitation operator, sorry, which is a sum of T1, T2, up to Tn, where n is the number of electrons, okay? And so thanks to this, you're going to be able to generate all the correction up to an infinite order, okay? So if you do a Taylor expansion of exponential t, you recover one, T1, which is the single excitation, okay? T2, that we're going to, so that's the double excitations, but you're going to have also this T1 square term, okay, which is going to give you the double excitation, which are the product of two single excitation. And that's those disconnected terms which are missing in CI and which makes the couplet cluster method size extensive. Okay, so they are very important. Okay, so the basic example is two H2 molecules very far away, and basically you meet in CI, you're going to miss this double, okay, and that term is going to be present in couplet cluster with this T2 square term, for example. So that's those disconnected terms, okay, that are going to make your method size extensive. Okay. So if I apply T1 and T2 to psi 0, which is the reference wave function, which is usually taken as a Hartree-Fock wave function, okay, but you can take anything else if you want. So if I apply psi 0 on T1, I'm going to get what we call a linear combination of the single excitations. So psi IA, so you probably know that for now, but so I took my reference wave function and I took the electron in occupied orbital I and I did put it in A, which is a unoccupied orbital, okay? And same for the doubles, so you have, you generate all the doubles, okay, here, and so those quantities here are really the key quantities in couplet cluster. That's basically the equivalent of the coefficient in a CI expansion, okay? So that's the amplitude, and that's the quantity you want to find, okay, the singles and doubles amplitudes to be able to compute the energy of the system, okay? And as a comparison, you have the expansion of the CI where you see that your ansatz is now linear, okay? Okay. So now I can write the Schrödinger equations for this couplet cluster wave function, okay? So H psi equal E psi, as usual. And actually what I can show by multiplying by exponential minus t on the left is that I can define a similarity transform Hamiltonian, which is defined as EH exponential minus t H exponential t, okay? And basically I'm able to transform that Schrödinger equation into a new Schrödinger equation for the reference, but now using a similarity transform Hamiltonian, okay? So the trick here is that actually, if you want to compute, you can compute a variational energy at the couplet cluster level, okay? You can compute like this. But what you're going to show is that if you want to compute that quantity here is going to cost you more than a full CI calculation, okay? And why is that? Is because that expansion here doesn't truncate, okay? You have an infinite number of terms, it doesn't truncate before you get to the nth limit of the number of electrons. So basically it costs you exactly the same cost, is the same cost as a full CI calculation. So what people have done is to compute the couplet cluster energy by projection, so projected couplet cluster energy. And so you take that similarity transform Hamiltonian or the Schrödinger equation equivalently, and you project that onto psi 0. And if you do this, you end up with this definition. And that definition is nice because psi 0 is equal to 1 usually. You can normalize it very easily. And that expression here is going to truncate very, very fast, okay? And all the power of couplet cluster is here, okay? And so here you don't have to compute an infinite number of terms to get the energy. It does truncate, okay? And that's how usually we compute the couplet cluster energy. So I can basically, I can write down explicitly the expression of that energy. And I don't want to bother you with this, but it does truncate fast, as I told you. It does truncate at the doubles here. And so you see that if you want to compute the couplet cluster energy at any excitation level, so it can be CCSD, TQP, and so on, well, the only thing that you need is basically the singles, TIA amplitudes, and the double amplitudes, TIJ. And for each method, you can get equations to be able to to get the value of those amplitudes. Okay, so that's the idea. So if I use a reference Hartree-Fock reference wave function, so my reference energy E0 over here is going to be just the Hartree-Fock energy. Okay, so I'm going to have some nice properties because thanks to Brillouin's theorem, I know that psi 0 do not interact with the singles. Okay, because I have an Hartree-Fock reference, so it's going to be 0. Okay, and I know as well that psi 0h psi ijab, thanks to Slater-Condon rules, are going to be given by those anti-symmetrized double bar 2 electron integrals that we talked about earlier. Okay, so the couplet cluster energy is just given by the sum of the Hartree-Fock energy and this term, which only depends on 2 electron integrals and the single and double amplitudes. Okay, so that's the singles and double amplitudes. That's the only quantities you need to find. Okay, so how do we do it? So we'll take a CCD. Okay, so that's one of the simplest couplet cluster methods for as an illustration. Okay, so I've got T just T2. Okay, and now I can I still have an infinite series because the exponential of T2 is an infinite summation. Okay, and I can write down the CCD expression like this, so sum of the Hartree-Fock one, and I'm going to have only the double amplitudes that now I'm going to call amplitudes times the 2 electron integrals. Sorry. Okay, so I've skipped basically the TIA, the single amplitudes. Okay, and now we're going I'm going to show you how I can design an algorithm to compute that energy, let's say, as efficiently as possible, at least simply. Okay, so now what I need to do, I need to find an expression, equations to be able to find the value of the amplitudes. Okay, so remember that I've found the expression of the energy by projecting the Schrödinger equation onto psi 0, and similarly to have to derive the expression for the amplitudes, I'm going to project that similarity transform Schrödinger equation onto the double excitations, IJAB, okay? So that's going to give me this, and I can rewrite this expression as what we call the residual equations here, that I call RIJAB, which are just 2 electron integrals, okay? So that's important, that's what usually we call the driver term. You have this delta IJB, which are just 1 electron energies of the molecular orbitals, so easy to do. You get that from an Hartree-Fock calculation. You get that from the Hartree-Fock calculation, and you can transform those integrals thanks to the algorithm that we talked about just before, the semi-direct algorithm, okay? The TIJB are the quantities that you're looking for. And here we have what we call a linear array, okay? Which means it's linear in terms of the t's, okay? And we're going to show that you can compute that in n to the 6. And you have what we call a quadratic array. So it means it's quadratic with respect to the amplitudes. And we can show that depending on the algorithm that you use, you can compute it as n to the 6 or n to the 8, okay? So at convergence, your couplet cluster calculation should tell you that those residuals have to be 0. So that's the condition of convergence. So a couplet cluster calculation, it's a nonlinear calculation, okay? So it's going to be an iterative process, exactly like the Hartree-Fock procedure, okay? So, so you have a different algorithm, but you're going to start with a set of TIJAB, which usually are taken from MP2, and you're going to refine those quantities, okay, to be able to converge to the optimized amplitudes that are going to give you the CCD energy, okay? So if I take that expression, because it has to be equal to 0 at convergence, okay, I can rewrite that as TIJAB like this, okay? So the only quantities I need to compute, so this one is easy, this one is easy, is the linear array U and the quadratic array V, okay? Is that clear for everyone? Okay. So now let's have a look at the linear array. Okay, so this linear array is just given by a bunch of 2 electron integrals times the amplitude. So you can check that it only involves linear amplitudes, so it's not the product of 2 amplitudes. And so you have different sets of 2 electron integrals. So you have what I call VV, so it means that 4 virtual orbitals, 4 occupied, and here you have integrals involving OV, so occupied virtual. So you can basically compute all those quantities separately, okay, if you want to do it nice. And here you have basically summation, 2 summations here, 2 summations there, and 2 summations there. So if I look at this, okay, and I think, I just have to look, and I know that it's going to cost me n to the 6, okay, why? Because I need to compute all I, j, a, b elements of u, so it's already n to the 4, okay? And I need to sum over CD or KL or KC, okay? So n to the 4, and each term costs me n squared, okay? So it's n to the 4 times n squared, it's n to the 6, okay? Which is the right scaling of CCD. So that linear term can be computed on n to the 6. Okay, so I'm happy with this. If now I'm looking at the quadratic array, the expression of the quadratic array, which is given by in the paper of Popol that I just gave you on slide number 2, okay? So if I look at it, it's given by a quadruple sum, KLCD, of those integrals, which are OOVV block, okay? And it's, you can see that it's indeed quadratic with respect to the amplitudes, okay? It has involved the product of 2 amplitudes, okay? Lots of them. And if I look at the formal scaling of that quantity, okay? So I have to compute all the I, J, A, B elements, okay? But I need also to scale to sum of a K, L, C, and D. So that's going to cost me n to the 4 times n to the 4. So it's n to the 8th calculation formally. Okay, and that's not going to be nice. Okay, I can tell you that if you write that program, your program is going to spend this entire time computing the VRA, and that's it. That's the only thing that your program is going to do, and you don't want that to happen. So again, we're going to apply this magic trick, which means we're going to sacrifice storage to gain in scaling. Okay, and we're going to define 4 intermediate arrays, x1, x2, x3, and x4, okay? And so you can see that x1 is going to cost n to the 6 because it's going to be, you're going to compute k, l, I, j, all the elements k, l, I, j, and you're going to sum of the c and d. The second one, only n to the 5 because 3 summation, 2 indices, okay? K3 n to the 5, 2 indices, 3 summations. And the last one, n to the 6, 4 indices, 2 summations, okay? And based on those guys, you can rewrite the previous expression, okay, as like this, okay, with those intermediate arrays. And here, magically, what you're going to show is that it only costs you n to the 6. Why? Because I need to compute all the elements I, j, a, b, and I need to sum over KL or sum over C. Okay, so I need to sum over KL or sum over C, sum over K or sum over KC, and this guy is n to the 5, this guy is n to the 5, and those two guys are n to the 6. Okay, so here, because the limiting steps are going to be the double summations, okay, IJ, KL, KL, or KC, so it's going to cost me n to the 6. So again, we use the same trick as before. We said it's too much computation, so I'm going to store intermediate quantities, and by doing this, I'm going to lower the scaling, okay? And if you do this, you're going to show that you're going to spend more time computing the V array, okay, than the U array, but you're not going, it's going to be the same scaling, so you're not going to spend the entire computational time doing this, okay? And you're going to be able to do CCD calculation pretty fast. Okay, so that's what I wanted to show you. So now we have everything we need to write an entire CCD subroutine, so in pseudocode. So basically what I'm going to do, I'm going to perform an Hartree-Fock calculation, and from it, I'm going to grab the 1 electron energy epsilon p and the 2 electron integrals in the NO basis. So it costs me n to the 5, okay, remember? I'm going to set my U and V arrays to 0, okay? I'm going to choose my starting values for my amplitudes coming from MP2, okay? They're given by this, easy to calculate. And I'm going to iterate until my the maximum value of my residuals are greater than a given threshold tau that I'm going to fix, 10 to the minus 4, 10 to the minus 5, okay? I'm going to compute my linear array, going to cost me n to the 6, okay? I'm going to compute my intermediate arrays k, x1, 2, 3, 4, okay, which are going to cost me at much n to the 6 again. From them, I can compute my quadratic array v in n to the 6, and after I can compute my residues and update my amplitudes, okay? And I can loop like this until my residuals are less than a threshold, and when it's less than a threshold, I can just compute the CCD energy, and that's it. So that's how you do a n to the 6 CCD calculation. And I think after that, I can recommend you a few books on this. So if you want a very gentle introduction to couplet cluster theory, you can have a look at Jensen's book. It's very nicely it's nicely explained and so on. It's not very difficult. It's very nice. Of course, if you want to know everything about Hartree-Fock calculation, please have a look at Szabo and Oslund's book, and probably Emmanuel Fromage's favorite book, Egaker, Jørgensen, and Olson, if you are more hardcore in second quantization formalism. And I think after I am done. So do you have any questions? No? I killed everyone with couplet cluster.
Well, I don't know, but thank you very much, Pierre-François. Can I just make a comment? There was a question about the density matrix and the MP2.
Yes.
Because actually, the MP2 energy is obtained from the wave function at the first order, and then there is no correction to the density matrix, to the 1 electron density matrix because of the Brillouin theorem. So actually, you need to go beyond you need to go through second order in the evaluation of the wave function to get the density matrix. So this goes beyond the MP2 actually method, if you want to get the density matrix. Ah, there is a question for you.
There is a question, yes. So could you explain more about the diagram in the last CC slides? Yes, I can. So if you write down the expression, so here, this expression here in terms of diagrams is basically the expression of the residuals, so the R's, in terms of the different terms in U and V, and actually those ones as well, okay? And so there is very nice papers about that. There is a book called, I don't know if I'm talking about it at the start. It's a book by Bartlett and Shavit, where you can find all those, the explanations for all those diagrams, okay? But basically, you can write the couplet cluster energy as a sum of diagrams, and each diagram, so you have different families of diagrams, and that can be very nice to know, because actually looking at the diagram, usually you can know the scaling of each step, but also you can design a couplet cluster algorithm for different classes of diagrams. And for example, if you only consider, let's say, the ring diagrams or the direct ring diagrams, which is one subset, you can recover, for example, what we call the RPA correlation energy. And if you use only the ladder diagrams, you can recover what we call the particle-particle RPA energies. And depending on the type of diagrams that you take, you can recover different methods from quantum chemistry and so on. But you can write formally any couplet cluster methods with diagrams. I'm not an expert in diagrams, but the book that I mentioned, you have all the explanations if you want. And most of the serious implementation of couplet cluster methods, for example, are based on diagrams as well, I think. So I don't know if it does answer your question.
Titu?
Yeah.
So thank you very much. I gather that you are going to do something very similar also for the GW beta-salpeter part, something because this could be interesting in our part of the theory, if you are also going to go in these details about the numerical part, the scaling, this part.
Yes, yes. Okay. So that's the plan. Yes, so my idea was to actually really like go into the details of the GW algorithm for at least for chemistry, and talk about which part of the calculation is expensive. Is it the calculation of the screening or the calculation of the self-energy? And after talk about maybe talk a little bit about Xavier Blas' implementation as well, which is contour deformation techniques. I don't know. I haven't prepared the slides yet, but yes, that's going to be the idea. And of course, beta-salpeter also like Cassida-like equation and giving the expressions and all the terms that we need to compute to do the calculations.
Yeah. Yeah, and this was my second question, in fact, about the Cassida equation, because I will mention that for the TDDFT, and you will cover the numerical and scaling part. Okay, thank you.
Right. Yeah. There is a question.
Yeah, there is a question. Sorry. Yeah.
Possible to calculate the max of ABIJ? Well, I guess you can. You just take the entire list and look for the maximum, but well, actually, I don't think it's very useful to know the maximum of ABIJ in absolute value. Yes. So you want to avoid calculating integrals that are small, but you really want to calculate integrals that are big. So I don't know any methods to calculate the max, but yeah, I don't know. So yeah, so for the second lecture in a few weeks, I think we're going to do exactly this, but for Green's functions methods, and try to. I'm going to try to give you the explicit algorithm, and hopefully, like in addition to this, you should have all the tools to be able to write your own code. And so I think that's something that students should do more, because writing your own code, actually it's possible. It takes time, but it's possible, and it really helps you to understand the details of the theory. So I think it's something that is very complementary with approaches like where you derive equations and so on. Being able to code them is something that is very important in our work, and that is going to teach you a lot about many different things. Oh, it's a question for Julien. For weak interactions such as van der Waals forces, which one can be better as standard MP2 or RPA CCD? So I have to admit that I'm not an expert in van der Waals forces. Which one can be better? I don't know. So RPA CCD. So CCD probably do better than MP2, I guess. RPA is just an approximation of CCD, so I guess it's not as good. But no, I can't really comment on this. I don't really want to comment on stuff that I don't know. So the CASPT2 implementation that I don't really know as well, but maybe some people know better than me, like Emmanuel. But I think the computational bottleneck is not exactly at the same spot, because CASPT2 does scale exponentially with the number of electrons, because you're basically going to do a full CI in an active space. So in CASPT2 type calculation, I don't think you worry too much about those integral transformation and so on. For example, in our lab, we do lots of what we call selected CI calculation, which are a type of CI calculation when you don't do CI, SD, TQ, and so on, but you just select determinants in the full CI space. And the method is fairly expensive, but that's basically the type of methods where you don't really care about storing the integrals or transforming the integrals, because the rest is so much more expensive that it's not really relevant. So if you have a code which works and it doesn't work fast enough for your purposes, so you should always try to identify where is the computational bottleneck. And the first thing you have to do is to kill it, okay? So if you run your program and you see that you spent most of your time doing a specific task, you should always have a look at that task and see why it does cost so much. And depending on the methods that you do, actually, the bottleneck is in different places, okay? And it's going to be very, very dependent on your on the way you have implemented the method. So at the very, very beginning of Hartree-Fock calculation, actually, most of the time was spending in the 2 electron integral calculation. And people have found some very efficient algorithm to do it. And after, you spend most of the time in calculating the Fock matrix. And after, you find some approximation, some new algorithm to compute the Fock matrix. And after, you spend most of the time diagonalizing the Fock matrix, because diagonalizing an n-square matrix costs you n cubed. Okay. So after, you have to kill that guy, because for a very large system, you're going to spend most of your time diagonalizing in the Fock matrix. And with time, you just try to kill the different bottlenecks. So when you write code, make sure you always write, you do some timing. So make sure when you write a subroutine, you print how much time you spend doing this. Okay, that's something that's going to help you in the future to make sure that your code runs fast and you know exactly where you spend some time computing stuff. You can do the same for the memory. It's actually a good technique to see if there is one part of the code that costs you a lot in memory. You can try to find some tricks to reduce the memory as well. Okay, I guess if there is no other questions, we might stop here.
So thank you very much, Pierre-François. It was really enlightening. Thanks. Thank you so much.
Yeah, thank you.
Thank you, all of you. And well, I'll talk to you in a few weeks for the GW and beta salpeter part.
Thank you, Titu.
Thank you. Bye.
Bye-bye.
Bye.